Good afternoon. My name is Chao from Nagoya Institute of Technology. It is an honor to have this opportunity to share my doctoral research here. So without further ado, let's get started. Well, my dissertation encompasses two parts: A, silyl-boron-mediated carbon-fluorine bond activation, and B, mechanochemical promoted fluorination and successive amidation. Now let's get into this. With the whole story of silyl-boron-mediated carbon-fluorine bond activation is about using the combination of silyl-boronate and base to activate a strong CF bond and functionize it, including three reactions: defluorosylation, defluoroamination, and defluorocarbon-carbon cross-coupling. And I'd like to start with the introduction of fluorine, specifically with regard to some pioneer works of defluorination reactions. For some of you might not know that fluorine is the 13th abundant element on Earth. Fluorine has 9 electrons, 1 fewer than neon, 2 electrons in a filled inner shell and 7 in an outer shell, requiring 1 more to be filled, which makes fluorine highly reactive due to its strong tendency to get an electron and reach a stable electron configuration. That means fluorine readily reacts with almost all other elements, including noble gases. Also, fluorine has the highest electron negativity among all the elements, making the bonds with other atoms strong. Furtherly, fluorination increases lipophilicity because the bond is more hydrophobic than the carbon-hydrogen bond, and this often helps in the cell membrane penetration and hence bioavailability. And because of these special physiochemical properties, fluorine compounds find applications in various fields, from home use toothpaste to advanced dental treatments, from small molecular hydrofluorocarbons to polymolecular teflons, in particular, drugs. This fluorine motif plays a crucial role in pharmaceuticals and agrochemicals, as it boosts the overall solubility and metabolic stability of the compound. It was reported there's more than 90 fluorinated drugs have been released in the past 10 years. And driven by the importance of fluorine motifs in such area, there's a growing demand for the development of unprecedented routes to access fluorinated molecules. Hence, the installation of aromatic CF bonds has attracted significant attention, leading to the exploration of new synthetic routes, especially these transition metal catalyzed or mediated cross-coupling protocols. As a result, tremendous aerofluorinated compounds have been developed. Because of that, aerofluorides become ideal building blocks for further transformations. Well, the problem is, though, that CF bonds are the strongest C heteroatom bond linkage in nature, which holds the high bond dissociated energy up to 526. It's extremely hard to break it here without hurting other weak bonds. Nonetheless, after many years of endeavor, several strategies have been developed. Let's take a look at them. Well, the first one is it's a classic nucleophilic substitution of aromatic fluorides. This addition-elimination sequence is only effective for these activated electron-deficient ions. One feature of this reaction is that the reactivity decreases in the order like this, which is entirely opposite from in the central reactions of the aliphatic halides. Here is an example. This activated halobenzene in the presence of pyrrole undergoes the SNR process to give this compound, and this fluorine substituted benzene got the highest yield among these substituents. The second one is a concerted SNR process. Different from classic one, this kind of reaction proceeds in the absence of activating group, but it usually requires stoichiometric strong bases or activating reagents. Like this. This reaction precedes the nucleophilic attack of the silyl involving this concerted SNR process to give the final compound. The biggest difference between these two reactions is that in a concerted SNR process, this Meisenheimer intermediate does not involved. CF bond could also be activated through ions. Using this lithium reagent, see with the loss of lithium fluoride, this ion intermediate formed, which can generate a mixture of 2 radioisomers with the nucleophiles. Taking advantage of this either 2 or 3 fluorodialanine react with the butyl lithium. The water gives the same product with a similar yield. And of course, there's a transition metal catalyzed CF bond activation. And just like Suzuki coupling reaction, it starts with oxidative addition to aerofluorides. And this step is difficult because of high bond energy of the CF bond, but people use the highly electron-rich ligands or high reaction temperature to make this step happen. Then this intermediate undergoes transmetallation, then reductive elimination to give the final compound. Like this, using nickel catalyst and electron-rich phosphine ligand at 100 degrees, this deep flow cross-coupling reaction was achieved. So in general, formal methodologies have these shortages: elevated reaction temperature, transition metal catalyst, a limited substrate, and etc. So to make some changes, we have devoted ourselves to this field for years, and we got several results, and which I'm going to present. Well, the first reaction is a defrosylation reaction. Well, this reaction is kind of a revised version of the one published in 2018. Well, in 2018, our group developed this nickel catalyst defrosylation reaction for the first time. Well, this reaction holds a general substrate tolerance, especially to these pi-extended systems. A year later, other groups reported similar reactions in the absence of nickel catalyst. Still, they got quite good results, which occurs to us that this nickel catalyst might not be needed for our reaction. So we reran the reaction under the same reaction conditions as before, yet without nickel catalyst. As we expected, we got a 65% yield product. Encouraged by this result, we continued to optimize reaction conditions. Here we can see from entry 2 to entry 6. In the same solvent, potassium is the best base for this reaction, and changing solvent did not increase the yield. By putting more equivalent of cyclobronate and base, we ended the yield up to 74% in entry 11. For entry 12, we used the same reaction condition in entry 11 plus 10% more of nickel catalyst. The yield increased from 74 to 83%. Well, this result suggested that this nickel catalyst does have a positive influence on this reaction. So with the optimal reaction conditions, we explored substrate scoop. As you can see here, moderate yield obtained in most of the substrates. And we did some comparisons to the reaction with the nickel catalyst. Obviously, there's a big difference in yield with or without nickel catalyst. We then proposed a reaction mechanism based on previous works. Firstly, this triethylcytobenzene reacts with the potassium to form this potassium anion complex with this part, which is then approached to aerofluoride to form this kind of intermediate. Then a concerted SNR process happened with the attack to this Bronsner by this potassium with a CF bond cleavage to furnish this related product, accompanied by the formation of these two kinds of potassium salts. So to summarize, we have revised this defrosylation reaction. Well, the chapter 3 is about the synthesis of triaromethanes by cytoradical-mediated cross-couplings of aerofluorides and aromethanes. Well, as we can see here, these multi-aero structures exerted crucial influence on drugs, and for years, several transition metal catalyzed cross-coupling approaches from these aero halides have been developed. Basically, there's two kinds of coupling partners of aero halides: this diaromethanes and the one with the leaving group on it, which can make this reaction easier. And I'd like to introduce some examples using this diaromethane because it's more related to our reaction. Well, in 2007, this palladium catalyzed triaerylation reaction was developed. In this reaction, both aerochlorides and bromides are suitable substrates. However, in terms of this coupling partner, instead of an ordinary diaromethanes, they intentionally use this aeromethane as a substrate because the proton here is a little bit more acidic than an ordinary diaromethane, which made this reaction feasible. And 5 years later, a more sophisticated reaction was reported. Compared to this one, well, this reaction condition is milder and the substrate scoop is broader. And to make it better, an ordinary diaromethanes are compatible with this reaction. However, neither of these two reactions, aerofluorides is suitable. So in 2018, this nickel catalyzed aerolation of aerofluorides was developed. was developed. The sad part is that in this reaction, only aryl-azaromethane are compatible with this reaction. Therefore, considering these previous works, we developed this carbon-carbon cross-coupling reaction of aryl fluorides and aromathanes. We started our investigation with using 4-fluorobiphenyl and diphenylmethane under the reaction condition in entry 1, and we got a 34% yield product, accompanied by the formation of this cell-related byproduct. In entry 2, we changed the solvent to THF. The yield increased to 49%. After that, source of base was tempted. Strong bases like teratoxic sodium or KHMDS did not increase the yield, while these weak bases just did not work at all. Well, from entry 7 to entry 13, we tried kinds of solvents again. Significantly, the solvent was found to be responsible for getting high yield. Not only did the use of diagram yield the highest yield of 95%, but also this diagram effectively suppressed the formation of this cell-related byproduct. The effects of diagram can be explained by the fact that this potassium cation would be encapsulated by diagram given a more naked and stronger base. And these control experiments revealed that no reaction occurred in the absence of teratoxic potassium or triethylcetobipene. So with optimal reaction conditions, we investigated the substrate group. Here we can see source of pi-extended systems. Fluorobenzene and methyl substituted fluorobenzene give a moderate to high yield. The lower yield of this kind of compound might come from the effect of steric hinders. This heteroatom containing substrate is also suitable for this protocol. We next examined the substrate group of these diaromethanes. Well, generally, these are products obtained with a good yield, including these quaternary structures. Well, the interesting part is that this dihydroanthocyanin, which usually acts as a radical inhibitor, is suitable for this protocol as well. To highlight the synthetic applications of this protocol, we examined the functionalization of couple of drug derivatives, and corresponding products were given with good yield. So to get a better understanding about this reaction, we did several control experiments. Firstly, we examined this coupling reaction in the presence of tempo. Here we can see with increasing amount of tempo, the yield product decreased. And this tempo trapped intermediate was observed and isolated. Well, this result suggests that this reaction involves a radical species. And considering that this cross-coupling of aryl fluorides by this tertiary benzoic organoboranates with teratoxic potassium at a high reaction temperature of 120 degrees via SNR process was reported before. And to eliminate this possibility, we therefore attempted the reaction of aryl fluoride with this boranated compound at a room temperature. And we only got 9% of desired product, leaving most of the starting materials. Well, this result indicated that this SNR process will not be included. In addition, the reaction of aryl fluoride and this cyclopropylbenzoate derivative was attempted. Well, this reaction didn't yield a corresponding product. Instead, this ring-opening product was isolated with a 26%, and this selected byproduct as well as this cyclodimer. To find out exactly what kind of radical generated during the reaction, we then carried out this ESR experiments. Well, and we successfully detected this triethylcyl radical and benzoylic radical. One more thing I got to mention is that the chemoselectivity of this reaction is kind of little poor. When a chlorine atom on the other end of this compound, and only 23% of these are product obtained, leaving this most of this borolated product. During this parallel experiments, here we can see basically only fluorinated compounds can be transformed into corresponding products. So based on our experimental results and previous reports, we proposed a radical mediated reaction mechanism. Firstly, this triethylcetobipene reacts with teratoxic potassium to form this kind of intermediate, which was previously confirmed based on DFT calculations. But in this step, due to the inherent repulsion of this complex, it splits into a sterically demanding frustrated radical pair with a homolytic adhesion of the SAB bond. Then this hydrogen abstraction from this diaromethane by this triethylcyl radical gives this kind of frustrated radical pair, accompanied by the formation of this triethylcyl, which by the way detected by GC mass. Subsequently, this frustrated radical pair attracts this aerofluoride by the interaction between fluorine atom and boron center for this transition state. And since the CF bond is activated by the interaction with the boron atom, this benzoic radical selectively attacks at the catalyst center of the CF bond the desired cross-coupling product obtained with the CC bond formation, accompanied by the release of these two kinds of salts. So in conclusion, we have developed this difluoro carbon-carbon cross-coupling reactions. With the chapter 4 is a transition metal-free cyclobronate mediated cross-couplings of organic fluorides with amines. Well, considering that amines irreplaceable role in organic synthesis, I skipped this introduction part. Let's just talk about methodologies. And this transition metal catalyzed emanation of from aryl halides. It's a very common protocol to get this tertiary amines. And there's 3 approaches are most effective and most used: this Ullmann type, Bottle type, and Matera-Photo redox. The feature of these 3 reactions is that the different transition metal was used. Like in an Ullmann type reaction, this copper is used, and in a bottled water emanation where palladium is used, and etc. And despite that, this aryl chlorides and bromides and nadides are suitable substrates in these reactions, but aerofluorides are exceptional because of that, because of their high bond dissociated energy. And still, I found some emanation from this unactivated aerofluorides, like this catalyst-free emanation reaction using this unactivated fluorine benzene and secondary amine under 190 degrees to give the final compound. Well, I got to say this reaction condition is too harsh to perform. And there's a nickel catalyst difluoro emanation reaction. Still, high reaction temperature is required, plus the usage of strong base. And of course, there are several difluoro emanation reactions out there. In general, these reactions either need a high reaction temperature or a transition metal or both or something. It's not good when it comes to environmental friendliness. Therefore, we developed this catalyst-free difluoro emanation at a room temperature. So with experience from previous works, we easily found out our way to optimize these emanation reaction conditions. As you know, firstly, we used 4,4-biphenyl, and in this case, methylaniline as model substrates to do this optimization part. In entry 1.5 equivalent of aniline in the solvent, this diagramming give 44% yield of product. When aniline was increased to 3 equivalent, the yield increased to 58%. When a suitable solvent, in this case, trigonum, was employed, the yield skyrocketed to 81%, while THF gave very low yield desired product. With an extended reaction time to 24 hours, the yield was further improved to 91%. And control experiments revealed both tetraprotic potassium and triethylcytopepene are dispensable to this reaction. From entry 8 to entry 12, varying equivalents of these 3 reactions did not improve the yield. So the substrate group of this emanation reaction was evaluated under the optimal reaction conditions. Likewise, this pi extended aerofluorides reacted efficiently with aniline, generating the corresponding product with a high yield. Even this steric hinderer author-substituted substrates. Also, both electron-donating and electron-withdrawing groups could be tolerated. And different from carbon-carbon cross-coupling reaction in chapter 3, substituents like chlorine, bromine, and nitrogen could be tolerated in this reaction. And this nitrogen-containing heteroaromatic fluorides was successfully difluoro emanated under the same reaction condition in even higher yield. While this cyclic amines and anilines show weaker reactivity given low yield. Moreover, this protocol could synthesize some drug derivatives, including this with deuterated methyl groups. We did several control experiments to gain insight into this reaction mechanism. As usual, firstly, we examined this reaction in the presence of tempo. Here we can see with the increasing amount of tempo, the yield product decreased. Well, sadly, we weren't able to detect this tempo chopped intermediate, but this reaction was sabotaged with an increased amount of tempo. Within the reaction of aerofluoride with this freshly prepared potassium analyte was in the presence of this organoboronate compound was conducted, yet no reaction occurred. So it can safely say that this process will not be involved in the formation of the potassium analyte. Furthermore, this deuterated methylaniline was employed in the reaction, and we got 84% yield products, and this deuterium exchange product wasn't detected. So we can this methyl group is not involved in the reaction. A clock radical experiment with the aerofluoride and this cyclopropylaniline was conducted, and we got when this reaction didn't yield the corresponding product, instead this aerofluoride was almost recovered, and this cyclopropylaniline disappeared given a complex mixture. When the reaction of methylaniline was conducted without aerofluoride, we got 27% yield hydrazine due to the dimerization of this methylaniline radical. These control experiments indicated that this reaction proceeds via a radical pathway. In addition, to evaluate chemoselectivity of this protocol, when other halide substituents were used, it turned out chlorine, bromine, and diene only get very low yield of these other products, which demonstrates this reaction and has an excellent chemoselectivity. Based on our previous works, once again, we proposed a similar radical mediated reaction mechanism. And just like I said before, this trithiocytobp reacts with the total potassium to form this intermediate, which then splits into this frustrated radical pair via homolytic serial of diacetyl bond. Then hydrogen abstraction from this methylaniline by triethyl radical gives this frustrated radical pair consisting of a methylaniline radical and boron radical, accompanied by the formation of this triethylsilane. Subsequently, this frustrated radical pair attracts this organic fluoride by the interaction between fluorine atom and boron center for this transition state. And since the CF bond is activated by the interaction with the boron atom, this methylaniline radical selectively attacks at the capital center of the CF bond the desired cross-coupling product obtained with the C-N bond formation accompanied by the release of these two kinds of salts. And this SNR process was ruled out by the control experiments I just mentioned minutes ago. So to summarize, we have developed this D4-CM cross-coupling reaction under mild reaction conditions. Here comes to chapter 6. Well, chapter 6 is a totally different reaction, which is about using this mechanical force to synthesize acids and then amates. Let's get down to the details. Well, these acids are carboxylic acid derivatives that contain a fluorocarbonyl group. And because of the electrostatic stability of the CF bond, acids shows both moderate stability and reactivity. And it is because of these unique properties, acids will find they can work as R source for coupling reaction, RCO source for acylation, and even fluorine source for fluorination. With the most straightforward to synthesize acids is to treat carboxylic acids with the deoxyfluorinating reagents. For years, many fluorinating reagents have been developed for such purpose. Although these reagents are incredibly effective as they are, drawbacks like thermal instability, the generation of a large amount of byproducts, somehow limited their utilization. Then we found TFE-DMA. TFE-DMA can be easily synthesized from this low-cost tetrafluoroethylene and dimethylamine. It is a little shame that despite the fact that TFE-DMA has been known for more than 60 years, the chemistry of this material was still limited to a few basic reactions. There's only one example was reported 20 years ago that TFE-DMA could deoxyfluorinate carboxylic acid to get acid fluorides, which encouraged us to find more about its deoxyfluorinating ability. We then carried out a couple experiments in batches here. It turned out both substrates bearing electron donating and electron withdrawing groups give high yield, while these sterically hindered substrates showed a low reactivity, even under double the reaction time. So to solve such a problem, we considered that bone meal might be a good choice. A bone meal reaction, in this case, a long story short, is to use mechanical force to accelerate the reaction process. And here's how it works. We put the starting material in this little jar with the balls in it and set it on this machine and shake it on a certain frequency horizontally like this. Using this kind of machine, we did the optimization part. Firstly, we ran a reaction with a little excess amount of TFA-DMA in the presence of dichromethane for 10 minutes. We got 78% yield product. It's good, but not enough. We then extended the reaction time, and here we can see there's no significant improvement on the yield. So we tried to run the reaction without solvent. The yield increased to 92%. When the 1.3 equivalent of TFA-DMA was employed, the yield was raised a little to 94%, which is the best reaction condition to this protocol. So under the optimal reaction conditions, we investigated the substrate scoop. Here we can see these two highly sterically hindered substrates were efficiently converted into corresponding products. Also, this bioactive compound, heteroarenes, and this aliphatic substrates were tolerated to this reaction. Even amino acid was suitable for this protocol, given excellent yield. And using such protocol, we then try to synthesize these peptides. And remarkably, sources of dipeptides were obtained with good to excellent yield. In the context of increasing attention to the problems of chemical pollution and resource depletion, the development of green chemistry was linked to a shift in environmental problem-solving strategies. One of crucial metrics to evaluate how environmental friendly a chemical process is the E factor. Well, the formula is E factor equals total mass of waste from process divides total mass of products. Apparently, the ideal E factor is 0, and higher E factor means more waste. Here's the standards. For bulk chemicals, tolerable E factors typically range from 1 to 5. In the fine chemicals, 50 may be acceptable. And in the pharmaceutical manufacturing industry, acceptable E factors may be more than 100. And here's an example of ours. Using our protocol to synthesize these peptides, and we got our E factor 1. And I'm not just talking about this one reaction. It's kind of common phenomenon for our protocol. So which demonstrates our protocol is quite environment friendly. So to summarize, we have developed this mechanochemical pro-molecule of fluorination and successive amidation reaction. In conclusion, using this cycloboron and base reaction system, we have developed these 3 reactions. Well, actually, more than 3. Anyway, and this mechanochemical pro-molecule fluorination and amidation reaction. And beyond their immediate applications, I hope the emergence of these protocols serve as a beacon of inspiration and guidance for future researchers venturing into the realm of cell bond activation. Well, thank you.
はい、ありがとうございます。それでは、質問。これ質問は日本語がいいですか？それとも英語がいいですか？
日本、とりあえず日本語でお願いします。
わかりました。じゃあ、コメントから来た、質問を言います。はい、このタイミングで、コメントしていただいても大丈夫なので、ぜひお願いします。じゃあ、チャプター1で、かなりいい反応ですねということなんですが、これはパラジフロロベンゼン、2つフッ素が入ったベンゼンなどの二環能性化合物にも適用できるのかという質問です。
そうですね。ジフロールベンゼンは基本的に その反応をやったことがありまして、基本的に2つの1個だけそのシリル化されます。
2つ目は入らないんですか？
入らないです。
あ
2つ目は入らないです。はい。
それは理由は何でなんですか？
そうですね。そこは、うーん、リここですね。
本当だ、本当だ。
はい、ここは基本的にそう、もしかしたら、その反応、基本的に最初は1個、そのシリル化されて、もしその時は、その後、そのシリルボランとそのタジャポトキカリウムも、もう、もう一回反応かけ、なんて言うんでしょうね。
ピュリファイした後に。
多めの、そのシリルボランとタシャルポトキカリウムを入れれば、多分2つ目も入る可能性もあります。
なるほど、なるほど。これは、一通りというか、そうですね。この条件だと1個入る。
はい。
なるほど、なるほど。ありがとうございます。あともう一つ、TFEDMA、メカノ反応の、
はい。
セクションで、
はい、
TFE が多分気体で、
そうですね。
ガスフェーズで、あと DMA もまあ気体だと思うんですけど、これは調整はどうやってやってるのかっていう。
それは、このような構成はね、その2021年にその論文で掲載されたやつであって、その TFDM 自体は構成してなくて、これはちょっと買ったやつです。
TFADMA で売ってるんですね。
はい。
なるほど、なるほど。じゃあそれを買って使ってるってこと。
そうです。
なるほど、なるほど。これいいですね、やっぱ。なるほど。ありがとうございます。あ
違います。
と、僕からの質問なんですけど、
はい。
チャプター、ちょっと何個か忘れたんですけど、
はい。
シリルヒ、シリルヒドリとか、違うわ。トリエチルシリルヒドリとか。
トリエチルボラン。
いや、と、あのアミネーションの
はい。
セクションで、脱離するのが、あの、SIH の、それです。右上でそれが出ると思うんですけど、これは、
はい。
この触媒サイクルってなんか悪さとかしないんですかね。これは反応しない。
これは反応しないです。
これは、
これは反応が終わった後、その GC で検出されてる。
なるほど、なるほど。そうなんですね。なるほど。いや、ありがとうございます。
ありがとうございます。
他、質問ありますでしょうか？僕は無限にしたいんですけどじゃあちょっとメカノの反応で、
はい。
これ、フッ素が入るちょっとメカニズムってすいません、示されてましたっけ？ちょっと気になって。
そのフッ素は、これ、メカニズムは書いてないんですけど、これは普通のその脱糖とか、フロリードみたいな感じで、脱酸素フッ素化反応になります。
これはどこのフッ素が、TFEDMA のどこのフッ素が入ってるんですか？
こちらのフッ素です。
そこなんですね。
はい。
なるほど。これ、じゃあ2回反応いくとかではなくって1個で止まる。
はい、1個で止まります。こっ
うん。
ちはその TFDMA の、なんで、なんか、こちらのフッ素が脱離して、炭素と窒素の二重結合になって、この円の形っていう平
なるほど、
行感があ
なるほど。
りまして、で、それでこ
あ
のフッ素がこちらのプロトンを1個、その温度計と反応して、HF の形で脱離して、で、その後は
円になると。
円になって、こちらの、酸素がこの TFDM の残りのやつと反応して、その酸素も抜けて、そのフッ素がこちらのアタックして、嗅覚アタックして、このアシドフロリドができます。
なるほど、なるほど。ちなみにこれ、平行、これはメカノなんですけど、もう結構完全に粉なのか、それともちょっと、
そうですね。
リキッドベース、ちょっとだけなんか液体が入ったりとかしなくて、完全に粉。
いや、その TFDMA が実は液体なんですよ。
これが液体なんですね。なるほど、なるほど。
そうです。
もう一回ちょっとコンディション見ても大丈夫ですか？
はい。
すいません。ありがとうございます。アディティブってそっかそっか、塩化メチレン、
は
DCM、
い。
なるほど、なるほど。じゃあ結構終わった後は、なんていうんか、ペースト状みたいな感じなんですかね。
その、 その原料によります。そのアシルフロリドがもし、そのできたアシルフロリドが固体の状態、固体の場合は、そのペストになります。液体の場合は、その完全な液体になります。
なるほど。液体の場合は、その液体で混ぜるよりもメカノの方がいいっていう風な感じなんですかね。
そうですね。普通はこの反応自体はバチの中でかけても普通に反応はいくんですけれども、まあ、ちょっと長めの時間が必要なので、
なるほど、なるほど。
で、そのメカノカミカル、ボールミルを使うと、わずか10分とか20分ぐらいでその反応はきれいにいきますし、あと、こちらの、特にこちらの、その立体障害の大きい物質だと、そのバチでは基本的に反応は、まあ、30%くらいいかなくって、そのボールミル使うと、まあ、20分くらいで、すごく反応はきれいにいきます。
なるほど、なるほど。ありがとうございます。
ありがとうございます。
あと、ジグライム、ダイグライムや、トライグライムが、廃止みたいに、なんか、アディティブ、溶媒かななんか、チャプター、3か4だと思うんですけど、ジグリムが良いっていう風な結果があったと思うんですけど、それです、それです。これは、まあ、なんか、廃止のような感じで働いてると思うんですけど、これはなんでこれの溶媒がいいんですかね。
これはそうですね。これはちょっと、僕たちもその確定な証拠はないんですけれども、まあ、あくまで可能性で、これのジグリムがこっちのあカリウムをトラップして、こっちのターシャルトキシンアニンをもうちょっと強い塩基性を与えるみたいな感じかもしれないです。
なるほど、なるほ
ど。TFT 計算をもうちょっとやっている最中なので、ちょっとはっきりとした理由はちょっとまだわからないです。
なるほど。すみません、もう一回メカニズムのところちょっと見ても大丈夫ですか。
はい。
なるほど。だからボロンに刺さるところの嗅覚性というか塩基性が上がって、なるほど、なるほど、ありがとうございます。あと、もう一個質問で、TFEDMA が、沸点が低くて、揮発性が高いから、少し使いにくいように気がするということで、
はい。
石川試薬ってことですか。石川試薬を使うといいんじゃないかっていう。石川試薬。
これですかね。
これですかね。はいはい。これが使いやすいかなと思ったんですが、試されたことはありますかという質問です。
石川試薬はこの反応に、メカノカミカルには使ってないんですが、普通にバッチでかけたことがあります。反応性としては、石川試薬の方が、もちろん反応性が高いです。でも TFDM は、まあ、分子量、一応、何で言えばいいでしょう。まあ、沸点はそんなに低くはない。揮発性は、僕は沸点は全然調べてないんですけれども、そんなに低く、まあ、揮発してはいないです。僕はいっぱい、なんか、なんだろうね、経験から。
なるほど、なんかほっといて、乾いたりとかそういうことはない。なるほど。
まあ、でも一応、これ、水と反応し、水が入る、水蒸気が入ると、HF も出るんで、そこはちょっと問題です。
なるほど、なるほど。一応、そう、石川試薬が、
ダストも基本的に一緒です。
いや、石川試薬、それじゃないらしくて、TFEDMA のメチルがエチルになって、で、フッ素がもうちょっと伸びた、プロペニルでフッ素がたくさんついたやつが石川試薬らしくて、
はい、
まあでも今回そんなに沸点が問題になってないってことはもうこれでも全然 OK というふうな。
はい。
なるほど、なるほど。ありがとうございます。
ありがとうございます。
他あればなんですが、とりあえずそうですね、ちょうど時間10分弱ぐらい経ったので、他になければこれでと思うんですけど、他大丈夫でしょうか、質問など。ちなみに参加してる山本君と修道君も質問できますけど
じゃあいいですか。
はい、お願いします。
僕、メカノケミカル反応すごく面白いなって思ってたんですけど、
はい。
で、反応の温度とかって急に上がったりとかしてないですか？ジャーの温度が上がるみたいな。
そうですね。その小スケールの反応をかけるだと、そんなに、一気に反応を上げ、反応の温度を上がることは、まあ、そんなには明らかではないんですけど、でも、僕らは1グラムの反応をかけるときは熱出ます。
あ
うーん。
でもやっぱりこの反応に関しては熱とかそういうのではなくてメカノケミカルな反応っていうのが極めて重要であるっていうことですよね。
そうですね。はい。
ありがとうございます。
なるほど、な
ありがとう
るほど。
ございます。
ありがとうございます。あと、修道くん大丈夫ですか？大丈夫そうですかね。あと、ちなみに追加で、さっきジグライムの話してたと思うんですけど、
はい。
あそこクラウンエーテルとかって試されたりしましたか？
クランエーテルですね。
はいはい。
ジグリムではなくて、ジグリムの反応ではやってないんですけれども、そのアミ
アミン、うんう
ノ化の、
ん
アミン化の反応でやったことがありまして、
うんうんうん
こちらです。この中には載せてないんですけれども、
うんうん
クランエーテルを、確か4等量を入れて、プラス、THF の溶媒化で、結構いい比率取れてます。
じゃあやっぱりカチオンターシャリブ
はい。
トキシカリのカリウムを取ってくるのがかなり重要なんじゃないかっていうふうな。
はい。
な
多分その
るほどなるほど。
可能性が高いです。
なるほどなるほど。ありがとうございます。
ありがとうございます。
はい。それでは時間ですので次に行きたいと思います。ジャオさんありがとうございました。あり
ありがとうございました。
がとうございます。